Okay, thank you, everyone. Today we have Omar Chowdhury from the University of Iowa. He is the Assistant Professor of Computer Science and also the co-director of the Computational Logic Center. He received his PhD from the University of Texas and the BSc from Bangladesh University of Engineering and Technology. Before joining Iowa, he was a postdoc research associate at Carnegie Mellon and also Purdue. His research focused on developing principled approaches based on automated reasoning techniques for analyzing and strengthening computer software and networks. His work has appeared in both top computer security and formal method conferences, including IEEE, S&P, ACM-CCS, NDSS, ACSAC, CAV, FMCAD, and RV. His research has been supported by both NSF and DARPA, including the DARPA Young Faculty Award. Today, he's going to talk about towards a high assurance and specification compliance X.509 PKI implementation. And I will pass the stage to Omar.
Thank you, Tiangu. I sincerely apologize for the delay. Thank you for your patience. I flew back from Bangladesh yesterday, and due to jet lag, I mistimed actually the time zone differences. So now, without further ado, I actually have a lot of slides. I may actually skip some of them. Today I'm going to talk a little bit about our group's effort from 2016 to develop a high assurance specification compliant X.509 PKI implementation. Now, so I will try to show you my journey of how we came to where we are right now. I don't think we are done yet, but this is our essential struggles and journey to the final goal of having a drop-in replacement of OpenSSL or GNU TLS with formal guarantees, formal correctness and memory safety guarantees. So, before I move on, I wanted to start talking about first, what is PKI and why do we need them? I might be preaching to the choir, but for the students in the audience, I wanted to give you a brief overview of what this PKI is trying to solve. So this is a classic problem of two parties trying to communicate over untrusted network, which may be eavesdropped by adversaries. In many cases, we talk about symmetric encryption, but then the problem boils down to how do we share keys. Now, if we share keys over that untrusted network, as anybody can understand, we do not have any confidentiality or integrity of the encryption. So you can have a man in the middle. So this is why public key cryptography was proposed, where each party has a pair of keys, one public portion and a private portion, where the public portions can be distributed and broadcasted, where the private portion is what is kept as secret. Now, the main issue is how do we distribute these public keys among different people? So for instance, if you set up a new computer that wants to talk to Google, how does they know what is Google's public key? Now, because if we were to just share them over this untrusted network, we could have a typical man in the middle attack where the middle party who's acting as an adversary shares their key and ends up impersonating each other, each of the communication peer to the other. So this is why the X.509 public key infrastructure came into play, where the idea is that you have some certificate authority, and so if somebody wants to get their public key authenticated by the certificate authority, they take this identity and the public key and pass it to the certificate authority some trusted channel. Now, this could be going offline to some other way, or say using SSL TLS certificates to actually SSL TLS connection to pass that information to the certificate authority. And once the certificate authority vets everything, they essentially use their private key to digitally sign a certificate. That tells you that this public key belongs to this identity. And this is the main focus of our study. Now, the obvious question one might ask is that, okay, so you're saying that we can use a certificate to verify somebody's authenticity of the public key. But how do we get the public key of the certificate authority to begin with? Now, for this, what we have is essentially you have this hierarchy. It's not necessarily like this. It could be distributed like a forest. And so you have different levels of certificate authority. On the top, we call them the root level CAs, which we, in a subset of them, we trust unconditionally. And they then vouch their trust on the intermediate level CAs. And the intermediate level CAs then vouches for the other intermediate level CAs or end host through digitally signing the corresponding certificate. Now, in many cases, when you install a computer or browser, the root level CAs, they come pre-installed. So whenever you're trying to communicate over Google, Google will essentially send you a chain like this. Now, this chain contains a bunch of certificates, which shows the progression of trust from the root level CA. Now, X.509 is used not only for secure communication, but in many other cases, when you have code signing, you have EAP TLS, which is for Wi-Fi connection, IPsec, email, and many other cases. Now, our focus would be in the context of SSL TLS. And so currently around 66% of traffic, which is much higher right now, this statistic is older, was currently being encrypted with SSL TLS. Now, a big portion of this would be contributed to Netflix and YouTube using SSL HTTPS in their communication. Now, the role of X.509 in SSL TLS is, as I mentioned, so whenever you're setting up certificate, the connection, so the server proves to the client that a certain certificate belongs to them. And this is where they also check crypto parameters before actually verifying the client certificate if needed. This is an optional stage, and then setting up a connection. Now, to put differently, the confidentiality and integrity guarantees that SSL TLS provide hinges upon someone being able to validate X.509 certificate change that the end node has provided. So you could say the X.509 authentication is the bedrock of SSL TLS confidentiality and integrity guarantees. Now, there have been a lot of work on verifying the correctness of SSL TLS implementation formally, but in many cases, they assume that the X.509 certificate validation process is correct. They make this assumption. But as we have seen in this slide, there are many different vulnerabilities that have plagued these X.509 certificate validation libraries, like OpenSSL, GNU TLS, just to name a few. Now, the main challenge is that the specification is in natural language, and they appear in this RFC called RFC 5280. And so it not only describes the format and structure of a certificate, but also specifies how, given a chain of certificate, you actually validate whether this chain of certificate is authentic or not. Now, the main challenge, as I mentioned, it's written in natural language. So you could have situations where the descriptions are somewhat ambiguous. This is just an example where it says that, so each certificate has a unique serial number that is assigned by the certificate authority. And so this one says the serial number must be a positive integer assigned by the CA. But the thing is, the non-conforming CAs may issue certificates with serial numbers that are negative or 0. certificate users should be prepared to gracefully handle such certificates. Now, one of the things about this RFC description is it doesn't tell you whether to reject a certificate with negative serial number or 0 serial number, or just don't crash. So we have ambiguities like this. Now, so as we were doing the work, we reached out to certain SSL TLS library developers. And one of the things they mentioned was that the X.509 validation is one of the most error-prone, code bloating, and compatibility nightmares in TLS implementation. Okay, so they find this to be extremely challenging. Now, you might say, like, okay, you have a bunch of certificates. I check digital signatures. What else there is to check? Actually, there are more to it than naked eye just sees at first glance. So the first thing is that each certificate comes with an issuer name, which are compound or complex structures. Say an issuer name has country, state, locality, organization, and other things. So you have to check that the issuer of the end entity certificate, Google for this case, matches up with the subject name of the previous one. So you have to match names this way. Then you have to check for validity. That is, a validity or an expiration date is given by not before date and a not after, which by itself is complex, as we will see later in the slides. And then you have extensions. Extensions are mechanisms for giving you flexibility of adding new features when needed. Okay, and these are the main challenging things of checking a validity of a certificate chain, along with checking the digital signatures. Now, so what is the problem of an implementation having like non-compliance with the standard? Now, you could have two corner cases. One would be overly permissive. In that case, your system can be subject to impersonation attack. To give you an example, say somebody might pretend to be Google, where they are an attacker. Or whenever you're overly restrictive, you might end up losing service. That is, you should have be able to connect to somebody, but you can't because the certificate is being rejected. Now, so at a high level, if you were to check the certificate chain validation logic, you can view this as taking a bunch of certificate chain and parameters like current time, the root certificates that you trust, and so on. And then it essentially needs to return accept and reject. In reality, it has to do a little bit more, but just for simplicity, you can assume that it just returns accept or reject. And in that case, you can view this whole process as a predicate. It's a predicate that returns true in case a certificate change should be accepted and false if it should be rejected. Now, as I mentioned, another different way of looking at it is that if you were to take all the possible input that this predicate can take, this predicate essentially partitions the whole input space into accepting universe, that is change that should be accepted, and a rejecting universe where the change should be rejected. Now, if we were to have a reference model or a reference implementation that tells us how to do this process or implement this predicate correctly, we could have actually gathered the reference universes like this, and then compared whether the implementation's universe matches up with the references universe. If that is the case, the implementation doesn't have any bug, it's correct. However, there are currently no reference model like this. And as a result of which, we couldn't do this process that I just explained. Now, so the question boils down to how can we check the non-compliance of an implementation in the lack of this reference model? And the second question we have to answer is, how can we actually obtain these accepting and rejecting universes from the implementations to begin with, okay? And then, so one of the things we can rely on is differential testing that has been used in software engineering and software testing for a long time. So the idea is that you feed the same certificate chain to two different implementations, and then you see whether the results are. So there are 4 possible cases. Now, in case they differ, you can assume or you can easily conclude that one of them is non-compliant, even though you don't know which one. So that you have to manually validate. Now, for the other case, you could have potential compliance. The reason we use the word potential here is due to the fact that both implementations may suffer from the same issue. In that case, they would agree on this. So based on this insight, now the question is, how do we actually obtain the universes? So the first approach is fuzzing. So you essentially generate a bunch of certificate chains, then you feed it to these different certificates, the implementation testing. And then you have your accepting and rejecting universes. Now, honestly, this is not such a great approach due to the fact that what you have are only sample points. If you have sample points, you might not have a thorough coverage of the whole input universe. On the other hand, one can actually use a symbolic execution where you feed a symbolic certificate chain to the implementation and run it through a symbolic execution engine. Now, what you will get is a bunch of regions, because the path constraints that you're going to get that are going to depend on the input will tell you, along with the return value, will create a region. So rather than having input samples of a region, you have the whole region expressed symbolically as a formula. Now you might say, Omar, there are holes in it. Why do you have holes in them? Because symbolic execution is incomplete. That means it may not be able to figure out all the regions. You might have holes that are in the region that you might not have explored. And so this is essentially an incomplete technique. So the first work I'm going to present to address this is Symcerts, and it was published in Oakland 2017, where the idea is that we use symbolic execution and we check X.509 small footprint libraries, specially built for IoTs. They tell you that it's a small footprint, and we want to check whether a small footprint means lacks security or not. Now, one of the things, this you will see over my research, is that just applying symbolic execution out of the box doesn't work. And in that case, to address these limitations of symbolic execution, which is the path explosion, what we do is we apply some domain-specific optimization and tweaks that allows this whole process to terminate in some feasible time. And finally, this approach that we're talking about assumes that you have the source code. So it relies on the actual source code. If you just have a binary, this is not going to work. Now, so the high-level idea is that you test the implementation by providing a symbolic input, which in our case is a symbolic certificate chain, and you extract, based on the output of symbolic execution, the regions in the universes rather than some samples that fuzzing does. Now, to give you a very high-level overview, or 10,000-foot of overview of symbolic execution, the basic idea is to generate automatic test cases of a given program so that it explores, you have a good code coverage of the code, and you want to do it completely automatically. And the basic idea is that you start off your program with a symbolic input. Rather than a concrete input that you consider in a fuzzing, you assume it can be anything. And then you explore the program in a symbolic fashion. So you would run the program exactly like you would run in a concrete case, but carrying symbolic values in your system state and memory. Now, the challenge comes when you hit a branch. In that branch, you actually don't know whether the branch should be taken because you did not make any assumption about the input. And so what you do is you would essentially fork, where you would consider both cases, where in one case where the branches were taken, in the other case, the branches were not taken. Now, in the case where the branches were taken, you carry the branch condition, that this condition was true. And then you essentially see whether there are some assertion failure or some interesting things going on, okay? Are there questions so far? Any questions? Okay. If there are no questions, then I'll move forward. So the basic intuition, which I'm going to go over really quickly, is that we collect path constraints from each implementation along with a return value. Okay. So what is the return value? And then what we do is we take a path constraint from one implementation that the return value is true, and then take a conjunction or logical and take a path constraint for that is accepted. Now, if you connect them with a logical and ask an SMT solver whether it is satisfiable, and the SMT solver comes back to you as satisfiable, you can say or conclude that there is at least one input for which the first implementation says no, whereas the second implementation says yes. And as a result, you found a non-compliance instance. And even the logic, the path constraints tell you what type of inputs would trigger this bug, okay? So I am gonna skip over the gory details, but I will be more than happy to answer more details during the question answer session. Now, we tried some small libraries, and what we did was that we extracted paths from these programs based on this symbolically constructed input, and then we essentially compared them using a path SMT solver. And as you can see, we found many different instances of non-compliances. Say, for instance, the AX TLS 1.4.3, we found 7 non-compliance. Note that this is not like what you'd find in fuzzing. In fuzzing case, you'd find particular inputs, whereas we found in these cases instances. That means if you were to solve the constraint over and over again, you can get many different inputs, concrete inputs, okay? Now, so I give you one example. So this is from SIA SSL. And so the basic idea is that whenever they're checking the alternate names OID, the object identifier, you will see that after decode, they are missing a break. Okay. So as a result of which, people who know about C's switch case statement, that even if it hits a particular case, in an absence of break, it would fall down to the next case. And now this is an example bug that you wouldn't able to find in using fuzzing that easily, because these are the kind of logical bugs that fuzzing cannot find that very easily. Now, the same thing goes with like how times are encoded. In time, so the year is encoded using 2 bytes, and the correct UTC time that is used for validity of the certificate is from 1950 to 2049. So that is, if your values are over 50, you assume that it's the prefix year would be 1900, whereas if it's less than 50, you would assume it's the prefix would be 2000. Okay. Now, if you see here, the way they kind of calculated this, we observed that some of these have a wrong range. Say, for instance, this matrix SSL one, you would have 1996 to 2095, whereas the correct range is from 1950 to 2049. So what this entails is that any certificate that expired in 1995, this code would assume it to be expiring in 2095. Now you might say, why is that a bad thing? It's a bad thing because crypto parameters that were considered secure in 1995 is not considered secure anymore. So as a result of which, you could just use Google's old certificate chain from 1995 and then use it right now. using this library, and this library wouldn't be able to tell a difference. Now, so what Symcerts does is that it uses differential testing, and without actually knowing the specification, you end up figuring out what are the different challenges and different non-compliant instances. And these are not like fuzzing bugs that you find by crash. These are not crash bugs. These are logical bugs. Now, for here, it's actually capable of finding more in-depth bugs than like fuzzing. And it gives you an accepting and rejecting region of an input using symbolic execution through the source code. But the two challenges that we faced over and over again is that scalability with symbolic execution is always an issue. The other thing is it actually doesn't check CRL, which is the certificate revocation list. And this is some ongoing work we are doing right now. Now, this concludes my first part of the talk. Is there a question I can help answer, or I should march on?
I have a general question,
Yes.
George, here. So you said that in the RFC there are already some parts that are not clear because they're in natural language, like what does it mean to gracefully handle some negative numbers. So in this tool, do you do anything for these parts, or do you go for the parts that are clear in the RFC and clearly specified?
So in many cases, yes, that's an excellent question. So once we find a non-compliance, because as I told you, both implementations disagree. So who's right? So for that, we actually consult the RFC. And in many cases, we do a manual judgment. So for instance, for this case, we assume that whenever it's a negative serial number, you consider it to be invalid and you do a rejection. That's the right thing to do. And so we used manual judgment to figure out these tie cases when we're doing root cause analysis. Does that answer your question?
Yeah, it does. Thanks.
Perfect. Okay, so the next thing I'm gonna talk about is signature verification. That is, one part of checking certificate validation is being able to check whether the issuer's signature is valid or not. And for this, we build a system called Morpheus. And so this is a joint work with my student Daniel and some other colleagues from CUHK. And so the basic idea is to identify whether there are weaknesses in the certificate signature verification implementation. Now, we are particularly focusing on RSA digital signatures, which is widely used in SSL TLS certificate, SSH, and IPsec. Okay. And in X.509 certificates, according to the Census dataset, which is an open source dataset that collects certificate from internet, 95% of them are actually using RSA digital signatures. So this is very important. Now, in RSA digital signature, you have this signature scheme that actually pads the message before you end up signing the message. So you have to prepare a message before you end up signing it. It's not like how we see in the textbook. And so this signature scheme is what allows to pad the messages. So one such example is PKCS #1 version 1.5 that tells you how to pad this message properly before you get ready for signature. Now, for this, there are many different cases where you would see that financially motivated actors were trying to break certificate percent to actually avoid detection. Now, our goal is to avoid such bugs. And for this, one thing we could do is we try different signatures and see whether only correct ones should be accepted. And bad ones or fake ones should not be accepted. That is the overall goal. Whereas if you have a bug in the code, you might have a situation that a buggy signature might be considered legitimate. So giving you a chance of signature forgery sort of attacks. And the other thing is you could have an interoperability issue if your implementation does not correctly adjudicate signatures to be valid or not. One signature might be considered valid by implementation, might be invalid by another. And in that case, if you're using, say, for instance, in the context of SSL TLS libraries, and you are using in server side one library and the client side another library, they may not be able to communicate anymore. Okay. And again, if you have these bugs, you can have signature forgery. That is, a bad signature that should not be accepted might be accepted by bug implementation. Now, our prior work, we did a little bit of work on this, has been working on manual efforts. So these are done by Bleichenbacher, who actually first came up with this signature forgery attack and explained it in a crypto romp session. And then Kuhn et al. In 2008 formalized that and increased the different type of cases. Now, so our work that we have done in NDSS 19 used symbolic execution. The idea is similar to what we used in Symcerts, but we needed to do some specific tuning to make sure that the symbolic execution scales for this problem. But they were limited by, the symbolic execution engine is limited by only CLI implementations, because the underlying symbolic execution engine we use, CLI, only can support C very well, at least at that time. Now its support has increased substantially. So our goal has been to kind of come up with an approach that is language agnostic. So the best thing to do would be to use a black box approach. Now, so what it entails is that, so in RSA signature generation, what you do is you generate a key, which is a public key has a pair, where one part of it, E, is the public exponent, and N is the public modulus. Whereas you have a private key, which is the private exponent. Now, whenever you sign a signature M, what you do is you first hash the message, then you raise it to the power of D, which is your private exponent, and take the mod N, and that's your signature. This is what you transfer. Now, given this signature S, the message you're taking the signature of, the hash algorithm you're using, and the public parameter, then the receiver should verify whether S is a valid signature of M. And the way it does it is like you take the signature, you raise it to the power of the public exponent, take mod N, and then you see whether it matches up with the hash value of the message that you're trying to take signature for. Now, but in reality, this is much more complex because the N, which is the public exponent, not the public modulus, is much longer than H of M, the hash values of M. And N, the length of N tends to be greater than or equal to 20448 bit. Whereas if you take SHA-1 or SHA-256, you only have 256 bits. Now, in that case, what you could do is that if you were to take a signature where the public exponent is 3, you could forge a signature by the following intuition. So your S3 mod N is the S cube mod N, when the public exponent is 3, is actually S cube, because N is much larger than S here. So what you could do is that what you entails is that the SHA-1 of the message is essentially S cube. So, and as a result, the S cube, because it's much less than N, doesn't wrap the N and do not have that the security you would want. So as a result, what you could do is you could essentially take the cube root of the forged message, the SHA-1 of the forged message you want, and then use that as a signature. So when you raise it to the power of 3, because it doesn't wrap, it will be considered the valid. okay? And these are the kind of attacks one can have if you're not careful. And to actually avoid this, what people did was that they pad the value of the message before they actually digitally sign it. And so this is how it works. So you build this padded message, which is the size of n, which is the public modulus. It starts with some leading byte being 0, and the block type tells you these are fixed values that are predefined. And then based on the hash algorithm you use padding bytes. And these padding bytes are represented by the byte value FF. And this padding ends with 0. And this padding byte length could be variable depending on the hash length, the hash output length. And then on the ASN1 DER info, this is where you encode the message along with the hash algorithm, because the receiver needs to know what hash algorithm you used. And so here you have hash algorithm and the different parameters, and the octet string contains the actual hash value of the message wrapped around in an ASN.1 DER representation, which is essentially a triple of the form type, length, and value. The type tells you what type of data it is, length tells you what the length of the data is, and the value tells you what the value is. So one thing interesting about this is that the type itself could be complex, that is a sequence type. And in that case, the value would be other type length value triples. So it could be nested in that way. And this is what makes it challenging to check this. Now, to figure out how much padding we need, so what you need is you need to know how much is the public modulus, and then you subtract the ASN1 decoded encoded message and subtract from it 3 bytes, the 3 corresponding to the hex 0001 and the end of padding byte 00. So that will tell you that this many padding bytes are necessary. And the other requirement is that the padding byte size needs to be at least 8. Now, if you look at this, if you just had a message, hello world, and you used your message, your public modulus to be 2048, you would end up with a message like this that you're going to sign. So before you sign, this is a K that you should prepare. Now, in that case, the verification is different because now you do not take the raise hash of m to the power of d, but you do raise k raised to the d mod n. And the verification is similar, where you take the signature, you raise it to the power public modulus mod n, public exponent mod n. And then you can have 2 approaches to validate. One is called decoding approach, where you say you decode this signature, the hash, and figure out whether it matches with the hash of the message. The other one is encoding based, where you actually create your own K based on the information you have, and then you see whether it matches up. So these are the 2 approaches of validating signatures. Now the problem is particular setting when the public exponent for RSA signature is 3, which is common for many resource constrained devices, you could, and along with some vulnerable PKCS implementation, which does not check, especially in the decoding mode, whether you have the right number of padding or the same, like right prefix or suffix, you could end up having a Bleichenbacher-style signature forgery. That is, somebody can create a fake signature that should not be considered valid, but these buggy implementations will consider them valid. And the vulnerable implementation often have these sort of unchecked bytes that you can hide in different places because the implementation does not check this. And in many cases, in low exponent mode, you could just do a little bit of search, including the cubic root, to actually generate a fake signature. Now, the problem we are trying to see is whether the implementation satisfies the standard specification. And the main challenge is that this specification of what is this right format is actually expressed in a context-sensitive grammar, and checking whether a given context-sensitive grammar is equivalent to the other is by itself an undecidable problem. Now, whereas we are given an implementation, which is a harder problem. So the implementation is non-compliant if we can find at least one instance such that the implementation returns that, yes, this is a valid valid signature, whereas the grammar says it's false. Or the other case where one says true, the other says false. Now, for checking non-compliance for I, what we do is we need to find a S where the S is not accepted by the grammar, but is accepted by the implementation, or the other way around. Now, the next question is, how do we represent this? And for that, what we do is we end up representing this as an oracle. An oracle is a formally verified implementation that we have generated. That is, we formalize what the specification wants, and we then implemented it and prove that the implementation satisfies the specification. And then we use this oracle as a representation of the gamma, which is the context-sensitive specification. But the challenge here is that the search space of signatures is huge. If you were to blindly go about searching and finding non-compliance, you won't be able to find them. And because the, say, signatures are like, say, 2048 bits, this gives you a search space of 2 raised to the power 2048. And if you have more, then you have more. So what we do is we do this adaptive combinatorial testing, which is aware of how a signature should look like. And when is that case that there are bugs? Now, for the oracle, we formalized the specification, then developed the PKCS1 implementation in Coq, and did the proof work manually in Coq. And then from Coq's extraction mechanism, we extracted an OCaml code that represents the actual oracle. And so the adaptive combinatorial testing, that are high level, what it does is that it actually divides up the whole structure into construct. And the basic idea is that if you were to break it down fine-grained enough, you can have a complex structure building up with smaller components. And the idea is to actually, as I show here, is there are 17 components in that input. And then you can essentially have for each component, what is the correct length and what is the correct value. And what is the correct position of that in the sequence of these components. And what we could do is for generating test cases is that you take these different components and you then try to mutate them. And you mutate them through some interesting values that you can consider. And then for the others, you retain the correct values. And based on this, you have a different set of test cases. And the second approach that we use is to actually check you have these different values, and then you try to see whether you can hide bytes. That is, your implementation is not checking whether that component has the right value. And if I can decrease the length by 1, that means I can hide the byte somewhere else. And you can try to hide the byte this way and generate test cases. Now, and the interesting thing is you can actually do a binary search on how many bytes can you hide into different components. And then that will allow you a way of signature forgery. So the intuition is the more bytes that you get unchecked, it's much easier to actually generate a fake signatures that will be considered correct by the buggy implementation. And then we compare it, all of these test cases, we run it into different implementations and the oracle. Now, if the oracle says no, but the implementation says yes, we have a bug, or the other way around. And in that case, we report the bug. And then again, as I mentioned, we do a binary search of figuring out what is the maximum number of bytes can I hide. And we keep doing this over and over again. So this is the whole approach. That is, you generate this test case using this test case approach, and then you need to pre-process. You need to pre-process because different implementations take inputs in different format. And then you call the oracle and also the target. If the results matches up, you're good. If they don't match up, then you report that this is a discrepancy. So we tested 45 libraries like this and written in 18 different programming languages. And we found 40 non-compliance in the different libraries. And 6 of them actually is susceptible to this Bleichenbacher-style low public exponent signature forgery. That is, for those, you can generate a signature that generally should not be considered valid, but these implementations assumes or adjudicates them to be valid. And we also found a library with buffer overflow, although our goal was not to find memory bugs. This is just like a pleasant side effect. And then we found 33 libraries that were suffering from incompatibility issues. And 8 libraries were having minor leniencies. They actually do not translate to any attacks, but they were just issues that goes against the specification. Now, I'm not going to walk over those implementations. And so I'm going to gloss over the results. So again, we disclosed all our findings to the affected vendors. And we were actually using this to test their implementations after we fixed them. And 12 new CVEs were assigned as they were immediately exploitable. Now, Chengwu, I have one more part of my talk. Now, because it's already 10, so it's up to you folks to figure out, to kind of decide whether I go on and talk about this last piece of work that I'm most excited about, or just conclude here and take questions.
Okay, let's see. I guess for how long is the last part?
I'm gonna take 10 minutes at max.
10 minutes, then let's do 10 minutes. I really want to hear it.
Okay, perfect. So let's do the last part. So the basic idea is, as I mentioned, one of our challenge is that our X.509 PKI doesn't have a formalized spec. So the idea was that we were trying to build a formally verified implementation, and for that we needed to have a specification. That is, what does it mean for a X.509 certificate validation implementation to be correct to begin with? Okay, now these slides I'm not gonna go over because we went over them. So again, the idea is to find implications of non-compliance. If you have overly permissive libraries, you have impersonation attack. When you have overly restrictive libraries, then you have interoperability issues. Now, as I mentioned, there are different approaches for testing this, differential testing being one of them, and dynamic symbolic execution, which is the Symcerts work, which I mentioned. Now, all of this work, the differential testing relies on, so it doesn't have a formalized spec, okay? It doesn't have any reference implementation, or you do not even have an oracle for checking whether if 2 guys differ, which one is right. So all of these were manual. So what we wanted to do is develop a high assurance implementation of the X.509 certificate chain validation logic. Now, the main challenge is that, as I mentioned, is natural language. It contains ambiguity and inconsistencies at times. And the other thing is that it's complex certificate structures. As I mentioned, certificates are expressed as TLV triples, T being the type, L being the length, and V being the value. And recall that the T could be complex. And in that case, you could have bytes being other TLV triples. The values could be other TLV triples. And so this nature of the length influencing the value being encoded makes this whole representation context sensitive. Now, so our goal was to re-engineer the specification and divide it up into syntactic and semantic restriction. Now, doing this is useful because the syntactic restrictions can focus on how certificates should be represented, and semantic means what it means for a certificate chain to be valid or not. Now, having this separation is good in the following sense, because you can have two different formalism for these different restrictions, which we used. And the other thing is that if we were to add certain things, or say add a new semantic restriction, then the syntactic restrictions leave untouched. And if you were to implement it this way, a library, your code would be much more modular. Okay. And yes, as I mentioned, you can have modularity in the specification, and you have two different formalism. Now the question is, where is this boundary? Because this is something, it's challenging. Say, for instance, in many cases, you could have a situation that this value should be 3. Now, is that a syntactic restriction or a semantic restriction? This is what makes it challenging. Now, the principle we used is explained through this example. Say, for instance, you have classic context-sensitive grammar, which is a raised to the power n, b raised to the power n, where n is a positive integer. That means you have equal number of a and b. This is the classic context-sensitive grammar. Now, you could have two situations. In the first case, you assume that the grammar representation is just the syntactic restriction is that you have one or more a and one or more b, number of b's, and the semantic restriction is that their numbers should be equal. Whereas on the other hand side, you have the whole thing encoded as a syntactic restriction, and then you do not have any semantic restriction. Now the challenge is that in many cases, if you do the left one, your parsing is very easy. Whereas if you do the right one, your parsing is hard. Now our goal is to find the sweet spot where you do not, and in the worst case on the right-hand side, the parsing complexity and the efficiency decreases substantially. So the idea was to find a sweet spot where we do not have ambiguity, but was able to have a easier parsing time, essentially having an efficient parsing and no ambiguities. Now, so for our case, the syntactic restrictions were all regarding DER encoding of the certificate, whereas the semantic restrictions are all rest, like signature should be equal, name should be equal, so on and so forth. Now, this is one example where it says, so you have a version field, which is an integer whose values could be 0, 1, and 2, representing versions 1, 2, and 3, whereas the semantic restriction could be, say, for instance, when extensions are used as expected in this profile, version must be 3. Okay, so this is an example of a semantic restriction. The same thing for key usage extension, where you tells you it's a bit string, where the different bit position tells you, so if the 0th position is on, that means it's this key was being used for digital signatures. Okay, and a semantic restriction could be when the key usage extension appears in a certificate, at least one of its bits must be set to 1. Otherwise, it should not appear. Now, for us, so this bit string is what the syntactic restrictions are, and the semantic restriction is essentially what's marked as the green box. Now, for the syntactic restrictions, we used attribute grammar. Now, and this attribute grammar is not the full power of attribute grammar, and we use attribute grammar with some limited context. So what we come up with is this limited context is this unambiguous LL1 context-free grammar, and then we add with it some context. And so the reason for this is that we can actually generate parser from it without needing to backtrack, okay? And when we talk about attribute grammar, we have both synthesized and inherited attributes, and this is domain specific for this language. For us, it's the length, like the length check, and also the value of a binary field. These are the two attributes we used. Now, for the semantic restriction, one of the things we observed is that it's a bunch of assertions. And so this gives you an executable specification. That means you just have to check a bunch of assertions. And so when we talk about executable specification, let me give you a quick example. Say, for instance, in many cases, specification can be operational, or non-operational, or executable. An example is whenever you say you are trying to define the what is the correct maximum function that finds out the maximum between two numbers, you could write something like, for all AB, max AB is actually, if A is greater than B, the answer is A, otherwise the result is B. So this specification tells you that it essentially not only tells you what, but it also tells you how to find it. Now, for us, what we saw is that all the semantic restrictions, they boil down to a bunch of assertions. And so an example would be your version should be either 0, 1, and 2. And if the key usage extension is present, that implies then the version number should be 2. And all of these assertions are represented as a quantifier-free first-order logic formula. And then we use an SMT solver to check whether the specification is consistent or not. That means whether our specification can be satisfied by at least one certificate, okay? Now, so the way we do enforce both restrictions is that the semantic restrictions are automatically represented as a quantifier-free first-order logic formula. For syntactic restrictions, we came up with a parser that we derive from the specification. And then what we do is that we get the concrete values. Say, for instance, version is 2 and the key usage extension is present. And then we combine the specification, the semantic restrictions, and these concrete requirements, and feed it into an SMT solver. And if the SMT solver says yes, we know that the certificate should be accepted, otherwise no. Now, this way, we just turn the specification into an implementation for free, okay? And in case the answer is no, so we can use the SMT solver to find this unset core. So this unset core tells you exactly where is the conflict. When certain constraint is not satisfied, it gives you a smaller formula that shows the evidence of unsatisfiability. And for our case, this essentially shows which RFC clauses is violated by the input. So this gives you a diagnostic information for free. So we implemented Ceres with Python, and as I told you, this is a modular implementation where you have the parser module, you have the chain builder module, and the semantic checker module, which are all driven by this driver module that actually pipes all the different components. And for our SMT solver, we use CVC4 because this is something is managed by the University of Iowa and Stanford jointly by our group. So we are very familiar with the SMT solver, and that's why we chose it. So we used it for two cases. So the first case, we used it for a non-compliance checking approach, where this implementation is being used as an oracle. That is, whenever two implementations differ, we use the SMT, the Ceres, or our implementation to figure out who's right. And then we also use existing chains to validate whether our approach is good or bad compared to the current implementations. And so we obtained 2 million certificates from the census dataset. and 2 million certificates from Frankenstein, and all of these are unique. So what we did was that we fed all of these certificates to 3 widely used SSL TLS libraries, and then also to Ceres. Now, what we saw is that Ceres was much more restrictive than some of these other implementations because we were being faithful to the specification. And some of these non-compliance issues like critical extensions were being missing, where GNU TLS suggests that it should be accepted or say version issues. When you have different versions, extension should be allowed in version 3, but there are cases in OpenSSL and GNU TLS, they actually allow you to have extension for other versions of certificates. So we reported all our findings to the 3 library vendors, and our findings were acknowledged by GNU TLS, and the other library did not agree with us, like the OpenSSL and Embed TLS. Now, this reflects the reluctance of the library developers on developing RFC compliant like X.509 implementations in general. Now, we do have limitations in the Ceres. This is not the end result. So our stuff is slower because we are using an SMT solver to do this simple checks. And we currently support only RSA signatures. We do not do any revocation status check, and we do not do any hostname checking yet. And we also do not provide any completeness guarantees because this is our interpretation of the specification and may not be reflected what is intended by the original designer. So to summarize, what we did was we obtained, we kind of re-engineered the X.509 natural language specification to partition it into syntactic restriction and semantic restrictions. And we formalized these restrictions. And from that, we obtained this high assurance implementation due to our executable specification. And then we used this as an oracle to do non-compliance testing and reported the findings to the corresponding libraries. And again, Ceres is publicly available. You're free to use them. And if you have comments, please let us know. And now I'm ready to take questions.
Okay, yes, great talk. So if anyone wants to ask a question, just ask.
I wanted to apologize for the like extra 15 minutes I took.
Yeah, that's fine.
Yeah, hello. Am I audible?
Yes, I can hear you.
Yeah, okay. Hi, Omar. Thanks for this very nice talk. So I have 2 questions. So one is, so for the Ceres part, the third part of your talk, so are you also like extracting it from the COG code that you did in the second part?
No, this is, again, this is not formally verified. This is just, so one of the things, okay, so let me try to answer it in a different way. Say, for instance, if you want to do formally verified an implementation, what would you do? So the first step is you formalize the specification. Okay. The second step is you check using an SMT solver or some other way that the specification is actually consistent. That means there are no conflicts. And the third thing you do is you actually implement it. And then on the fourth, you use some technique like interactive theorem proving or deductive verification like Daphne to show that the implementation actually satisfies your specification, right? Now, the beauty of this work is that after doing number 2, which is checking consistency, we realize that because of the kind of things we are checking, the specification by itself can turn into implementation, right? And this is what Ceres does. And it's not extracting or it's not formally verified yet. It's just that the specification is being executed rather than you having a different implementation and proving that the implementation satisfies the spec.
Yeah, I see. Okay. Yeah, thank you. And the second question which I have is, so which is also related to Ceres. So the way you motivated and the examples that you gave for the grammar, so they all looked completely context free to me. So for example, you motivated with the standard example of A to the N, B to the N. That is a context free grammar, right? Not a context sensitive one. So are there cases which are actually a part of, like of the specification, which are actually context sensitive,
Yeah,
and
so
that
I
you
mean,
did not go through in your talk today?
yeah, so there are, you have sets, that is issue. When you have sets, you have to make sure that something do not actually repeat. Then you have other restrictions like you have conditional requirements that if a certain thing is X, the other thing needs to be Y, right? So if you were to implement the whole thing as a syntactic restriction, this becomes context sensitive, right? Does it make sense? Okay, so let me.
Yeah. Do you have a concrete example from something from the specification which is actually context sensitive?
Okay, so one of the thing that you have to check is that, yes, so say for instance, you have root level TLV, the type is sequence, okay? And then what you have is that your V, that means are a sequence of multiple types, okay? And the length tells you the length of all the types. Now, if you think about just context, you have to carry the root level L to be able to see whether that any of the tuples that you have in the top level value does not exceed the extended length. Does that make sense?
Yeah, yeah.
So this
Okay.
is where the context sensitivity comes from, that you have to carry this length, and you can have nested sequences. So you have to you have to carry these lengths.
Yeah, okay. Yeah. Thank you.
Yeah, welcome. Other questions?
So let me stop live streaming to see whether there are off-record questions.
Sure.
Okay.
So I have another general question if there are no other questions. So thanks, Omar, for the talk. It was very nice. What the question is, how much work would it be, and I'm asking for a high level estimate now, to change this work to a different signature verification scheme if people drop RSA verification, for example, they choose something like DSA or elliptic curve DSA or something?
So yeah, that's an excellent question. So it's actually so for the Morpheus work, the approach would be fairly different. Like it would require to rework everything. It's not reusable for the following sense. So the benefits that the efficiency benefits of testing that comes from Morpheus is due to how we actually specialized it just for PKCS 1. It's not for general certificates. So it's very geared towards that. Now, if you want to do elliptic curve, you can use a similar approach, but all the details have to be reworked. So you cannot use this approach verbatim. So you can, the general approach would be similar, but all of the pieces need to be reworked. Like say for the Oracle. So the Oracle needs to be reworked because it's a different specification. You might use the further, but all the restrictions you have, you need to actually change them. So we hard-coded the restrictions, like 17 components. So your signature scheme, the elliptic curve might not have signatures or say 17 components, right? It might have different components, and the components might have different restrictions. So yeah, I mean, it has to be changed substantially, unfortunately.
Okay, but I mean, people starting from an RFC or some similar specifications, they could go through similar steps and then
Right.
change the appropriate place. Okay, thanks.
Yeah.
Okay, are there any other questions? Right, if not, then let's thank the speaker again. It's really a nice talk. At least for me, it's a very interesting topic.